Okay. Did it tell you recording in progress? Yeah. Okay. It doesn't tell me that. It just tells you that. Okay. Nice to know. Okay. So last time we talked about the second quantization way of formulating the problem of Bose-Einstein condensation for interacting bosons. So let me just remind you where we started. What we did was we wrote down the Hamiltonian for the system as a in the second quantized form. So we simply wrote down annihilation creation operators. We spent a bit of time discussing how to write down the potential energy of pairwise interactions between the bosons. And the way we did that was writing it down in terms of a density operator. And then what we saw was that if we write down simply the convolution, the sum of particles of the pair potential without any constraints, we can write that down in terms of operators, and that's shown on the top left. But what we discovered was that if we write it down, there's a term that is divergent, and that term comes from the interaction of particles with themselves. And so if we want to subtract that, what we have to do is make sure that the creation operators are always to the left of the annihilation operators. And this is what people who do quantum field theory call normal ordering. And so we explained the physical significance of that. And so we end up with the potential shown up here on the top left. We now have correctly removed the self energy. Then what we did was we wrote down the Bose-Einstein condensation. So we just said if I have non-interacting bosons, they're all going to be in the we're much where actually 1 second. One of the students just texted me. I'm just going to send him the information. Okay, sorry about that. So then we saw that we can just write down what Bose-Einstein condensation looks like, and then the question is what happens to Bose-Einstein condensation when you have an interacting system. And so what we did was we said we're going to just take the potential energy and we're going to replace it with a pseudo potential. So we're going to pretend that the particles are point particles. The interactions will happen when they're at the same point in space. And so we can think of the interactions being some factor that is proportional to the a delta function. And the way we can justify that is by saying we're looking at the system at large scales. And because we're looking at large scales, the particles look like points, so we can't see all the details of the wave functions inside the potential well. All we see is the behavior of the particles at long distances away from the interaction where they're plane waves. And so in that case, then we can think of the potential energy as being just a delta function. And then what that means is that all we see far enough away is the S-wave angular momentum scattering states. And so I told you, but I didn't prove it. It's quite complicated, that the potential energy magnitude U0 is related to the S-wave scattering length, which is in some sense you can say is related to the cross section of the particles. Okay, so that's what we did last time, and that approximation is called the pseudo potential approximation. So then we did something else, which was we pointed out that the condensate behaves like a classical field, even though we are starting off with a description in terms of quantum operators. And the reason for that is because you have macroscopic occupation of the ground state. And so what that means is that the operators that create and remove particles from the ground state essentially commute, as shown here on the top left. And so what that means is we can write down the total number of particles in the system as a complex number plus a Fourier component of operators. And so that is the simplification that we are going to use. So we're going to describe a quantum mechanical macroscopically occupied ground state as being a classical variable. And the reason we can do that is because there's such a huge number of particles in that ground state that we have a small parameter, which is 1/n. So then we started off doing perturbation theory in the magnitude of the operators, the annihilation creation operators compared to the macroscopic condensate. And we know that they're going to be small because the annihilation creation operators add and subtract one particle to the state, whereas the condensate is composed of n, a thermodynamically large number of particles. So we can do perturbation theory, and we started to do that. Step one was just to write down any sum over k in terms of the complex conjugate, the complex number big A naught plus the sum over k states which are not at k equals 0. And then we went to writing down the Hamiltonian to second order in those terms. And that led us to the form that you can see here on the left-hand page, where we are simply looking at the Hamiltonian to second order in the operators. And again, because they're so much smaller, then the occupation number of those states is so much smaller than the occupation number of the ground state. Then what we did was we rearranged this form for the Hamiltonian, and so there's nothing particularly interesting in that. But we replaced the operator in the ground state A0, the condensate occupation number, with the total number of particles in the system, and so we ended up with a form that is shown at the top of the left-hand page. Okay, now that's all well and good. What we actually want to do is we want to diagonalize this Hamiltonian, and we can see that the first two terms have a simple physical interpretation, but the term at the top right, the third term, does not have an easy interpretation, and that's what we're going to do next. So we made the first step to do that last time, and we're going to finish that right now. So what we did was we said, let's introduce new operators defined at the bottom of the page. Alpha k defined as I've written down here with a very obvious typo. Let me correct that typo. So there's the typo corrected. I just corrected it in my notes. Sorry about that. And the next equation also has a typo. Well, it's not very good. Let's write it like that. There we go. Okay, so I corrected the typos. I think I just wrote it in the wrong place as I was writing. So those are these alpha operators. They're a linear combination of the annihilation and creation operators with two unknown variables u and v, which are functions of k, and we're going to determine those functions during the course of this calculation. So what we are going to try to do is we're going to try to express the Hamiltonian in terms of these operators. And to do that, we have to write down the Hamiltonian not in terms of the A operators, the boson creation and annihilation operators, but in terms of these new operators, these alphas. And so at the end of last lecture, what we did was we figured out a way to express the A operators in terms of the alpha operators rather than the alpha operators in terms of the A operators. So what we have down here is the alpha operators in terms of the A operators, and then we eventually worked out what are the A operators in terms of the alpha operators, and that's shown over here. And all we did was we basically multiplied the definitions by VK and UK respectively, sent K to minus K. There was another typo that I made last time, which I realized afterwards. And then in the end, you get the equations written down at the bottom of the page on the left-hand side. Okay, so what are we going to do today? We're going to start off by looking at those operators, these alpha operators, and we're going to ask what is the physical interpretation of them. And we're going to see that they have a very nice interpretation, namely that these actually are themselves bosonic variables. They create particles, and we're going to eventually see that these particles are the quasi-particles. So that's the first thing. Then we have to understand what is these functions u and v, these mysterious functions that we introduced in this calculation. And we've got two functions at each value of k, and we've really got one constraint. We used one constraint, uk squared minus vk squared equals 1. That's there on the left-hand side of the page near the bottom. That constraint enabled us to find a unique inversion of the definition of the A's and the alphas. We have another constraint that's going to come, and that's going to arise because we're asking that these things represent quasi-particles. And you're going to see that once we have that constraint, then that uniquely determines u and v, and then we can literally diagonalize this Hamiltonian and put it into quasi-particle form. Once we've done that, we're going to compute the excitation spectrum. We're going to see that there are phonons and modes that describe sound propagation. And I'm going to show you that all these effects are many-body effects arising from the interactions in the system. Then at the end of the lecture, if I have time, we'll get on to the next topic, which is looking at what happens to weakly interacting bosons at temperatures greater than 0. So everything we're doing last time and today is all at 0 temperature. All right. So now that we've said that, let's get moving. So what we're going to do is in my calculation, I'm going to do step 3, and what we're going to do is we're going to identify the nature of these alphas. So what we're going to do is we're going to look at their commutation relation. So what we're going to simply do is we're going to compute alpha k dagger, and we can write that as the following form. So this is UK AK plus VK A minus K dagger, and then UK AK dagger plus VK A minus K dagger. And no dagger there. Okay, so that's just by the definition. And then we know how the A's commute. So this we can write as UK squared times AK dagger plus VK squared A minus K dagger A minus K. And those are the only terms that arise that are non-zero. And so that we can write then is equal to UK squared minus vk squared. And this quantity uk squared minus vk squared, this is what we used last time to ensure that we could invert the relationship between a's and alphas, and so therefore this is equal to 1. So what I've just shown you is that the alphas are bosons. So we represent particles, and we can think of them as being bosons. So now let's have a look at the Hamiltonian itself. So step 4, which is going to be quite non-trivial, is we're going to now construct the Hamiltonian in terms of these A's. So we know what the Hamiltonian is in terms of A. Now we're going to try to construct it in terms of these alphas. So what do we actually get if we do that? Well, just to remind you, what we're aiming towards is the following. What we're hoping to get is something in quasi-particle form. So we know that the ground state energy of the system, I already derived that last time, was U naught n times n, and this little n here is n over v. And that's the ground state energy. Then we are hoping what we would like to have is something of the form sum over k not equal to 0, and then something that we don't know what it is, some energy spectrum times alpha k dagger alpha k. So that this would be then the number operator of these alpha particles, these quasi-particles, and then there'd be something else. That's what we're aiming towards. If we can get something like that, then we can say, well, these particles are non-interacting particles, and we can interpret them as quasi-particles, and we can calculate what the energy is. So now the question is, does the Hamiltonian actually have this form? So that's the question. So how do we answer that? So the strategy is take A, the AKs are some function of the alpha k's, and then we put those into the Hamiltonian written down as a function of the A's. And then from that, we will then get the Hamiltonian in terms of the alphas. So that's what we're going to do next. And so I'm going to do the algebra for you. So there's nothing literally more complicated than simply taking this form, these equations over on the left here for A, and plugging them in to the Hamiltonian that you can see over here on the middle of the page. So we're going to take this Hamiltonian, plug in these alphas, and see what we get. So if you want to understand this, I invite you to do this calculation yourself. But I'm going to write down the answer, and it's going to take me a few minutes to write it down because it's really long and there's lots of terms. So let's get started. So what we get is the following. So we get a half U naught times n times n. And then we get a term that looks like this. Okay, so that's the first term. So there's a constant piece that we already found, and then there's a term that now involves the u's and the v's, but there's no annihilation and creation operators in there. So this is just going to be some number that we're going to have to end up calculating when we sum over the dummy variable k. Okay, then we have another term, and this one looks like this. Okay, h bar squared is equal to m plus n u naught uk squared plus vk squared minus 2 u naught n uk vk. So we have that, but now this thing is times alpha k dagger alpha k is alpha minus k dagger alpha minus k. So let me just make sure, so I've got that is correct. And then lastly, I have this term plus, these terms gradually get longer and longer, plus 1/2 sum k not equal to 0 u naught n Okay, so I've written down all the terms. So let's have a look at what we have here. So the first term, it does not involve the alphas at all. The second term, so so it's just a number that you can in principle compute. So we can if we knew what u and k, if we knew what u and v were as a function of k, we could just go ahead and compute that term. It would be a sum over k, which we would turn into an integral over k, and then we would just do the integral. So that's what we would have then. Then we have a term that has some numbers in terms of u's and v's, and then that's multiplied by alpha k dagger, alpha minus k dagger, alpha minus k. And that term, the one I just underlined, that looks very familiar to us. That's just the number operator. So this term we can interpret, and it looks perfectly reasonable. So this is a term that we like. And then we have a third term, which has a bunch of u's and v's, which we don't know what they are yet. And then it has a term alpha k dagger alpha minus k dagger. This term is some kind of anomalous term. And this term we do not like at all. This term we have no interpretation of what that means. And the reason I'm putting an X by it, and I'll even put an unhappy face next to it, is because this term is not of the quasi-particle form. So this term here, this term is not of the quasi-particle form, and it is hard to interpret. So, and then finally, we have terms of order alpha cubed. These are the terms that we've neglected. That's perfectly fine. We know that we're doing an approximation here in terms of the occupation numbers of these excited states compared to the ground state. So we're not worried that we've got these other terms that in principle are there. So what do we do? And the answer is, what we're going to do is we're going to say the following. Since we have this this term that we don't like, what we're going to do is we're going to take the coefficient of that, which is the term that I just underlined over here on the left, and we're going to set that equal to 0. And by setting it equal to 0, we're now going to get a functional relationship between u and v, and that will be the second constraint that we use. So let me write that down. So of these terms, the last term is what we could say is anomalous, and we do not know how to interpret operators like alpha k dagger, etc. Okay, so what we're going to do, so the strategy is to set the coefficient of this anomalous term equal to 0. So let's go ahead and do that. So that means that we're saying that u naught times n uk squared plus vk squared minus 2 uk vk times h bar squared k squared over 2m plus n u naught, that has to equal 0. And that's true. That's another constraint. Remember, we also have the constraint we had before, which was that uk squared minus vk squared is equal to 1. And this was the constraint. We also had invertibility, we had this constraint. And so the end result is that what we have then is two unknowns at each value of k, uk and vk, and we have two equations. So that's good. And so now we have to solve those. So the next thing we're going to do is we're going to solve these two equations. So there's lots of ways that you can do it, and I'm going to show you a way that's particularly useful and convenient. So the best thing to do is to use the constraint that uk squared minus vk squared equals 1. And so what we are going to do is we're going to take the constraint and we're going to say let uk be defined as the hyperbolic cosine of some new variable cosh of k, and vk be defined to be shun of phi k. So if those things are true, then this automatically gives us the equation star, that uk squared minus vk squared is equal to 1. So if we have that, then now we have to look at the equation square. So what does equation square become? So that becomes now, in terms of the phis, it becomes the following. U naught n times cosh squared by k plus sine squared phi k is equal to 2 cos phi k sine phi k times h bar squared k squared over 2m plus a u naught. So that's what we have. And what we want to do is we want to solve this for phi. And once I've solved for phi k, that then gives me uk and vk. So this equation looks a bit of a mess, and it is. So what we do is we use the following double angle formulae. So remember that 2 cos phi sine phi is equal to sine 2 phi, and cos squared phi plus sine squared phi is equal to cos 2 phi. So we can use those facts to then simplify this equation. So what that then tells you is that if I take u naught times n over u naught times n plus h bar squared k squared over 2m, and that is just equal to the hyperbolic tangent of 2 phi k. Okay, so that's what we have, and we're looking for a real solution of this. So what that means is, if we're going to have this as a solution, we need to have u naught greater than 0. So for real solutions, we need u naught to be greater than 1. And if u naught is greater than 1, then 10th is between -1 and +1, and so we can find a solution. So let's just have a look at what it looks like. So here on the horizontal axis, I'm drawing a phi k. Tan for phi k goes between 1 and -1. So I can draw that like so. So something like that. And then the solution for this equation exists if the value of u naught is somewhere in the middle here. So let's suppose then I draw the value of u naught n over u naught n plus h bar squared k squared over 2m. So that's a number that is between 0 and 1. And so it looks like that. And then the actual solution occurs over here, where these two things are the same, and that gives us the solution of phi k. Okay, any questions about this so far before I go on to finishing the calculation?
Remind me of the range of UK and VK. Why is this between -1 and 1?
VK isn't, but tanth is between -1 and 1. Okay.
Oh.
So if you look at look at this equation star on the top right hand side. So what I've got is that tanth of 2 phi is equal to this ratio of u naught n over u naught n plus h bar squared k squared, and that just
yeah.
Right, that just comes from over here on the left hand side. all I did was replace the two cosh shine by shine and the cosh squared plus shine squared by cosh and then divided, and that gives me a hyperbolic tangent.
Oh yeah, I guess my question should be, why like UK is larger than zero, yeah, or something like why you can construct the parameterization of UK and VK based on quotient, yeah,
Well, because of this equation up here, because
yeah.
UK squared minus VK squared equals 1, so I can satisfy that equation if U and V are functions of another variable that is like that.
Um, but in
So
that case, you actually constrain the range of UK and VK.
I do, I do. I constrain the range, and then now we're going to see if those things are real or not. So we've said that U and V are real and spherically symmetric. So
Okay,
we already decided that. So they're not complex. They don't have imaginary parts. So for them to be real, they can be written as cosh, and then the phi's have to be real as well. And so
okay, thank you. Yeah,
okay, so
okay,
I've used that to, in other words, if U naught was not greater than 1 but less than 1, then it would not lie within the range -1 to +1, and then the phi's would be complex, and the U's and V's would be complex.
okay, thanks.
Okay,
Uh,
any other questions before I go on?
yeah, one quick question on the same point. Since we can parameterize U and V as Cosh and Stinch, then our original transformation defining the alphas, it looks like a hyperbolic rotation of the A and
Yes,
A dagger operators.
that's
So
correct.
can we interpret in some sense that the creation and annihilation operators are existing in some sort of hyperbolic space, or is that reading too much into what's happening here?
Well, you might want to do that for all sorts of obvious reasons.
Right.
Um, but I don't know.
Okay.
Let me just mention that if you are doing this for fermions, so if you
Mhm.
are doing this for the theory of superconductivity, and I'll send you out a homework sheet, which I don't,
Mhm.
well, I'm not going to ask you to do,
Right.
but you can look at it. Then you will find that you don't get this. That
I see.
that in fact the analog of this is UK squared plus VK squared is equal to 1.
And you get a Euclidean rotation.
Yeah. So
Okay.
it's just exactly, it's not hyperbolic.
Okay.
So I don't know if there is some other geometrical interpretation of this
Mhm.
beyond what you can see in this algebra.
Okay. Thank you.
All right, so let's carry on then. So now we want to actually solve these equations in U and K, U and V, I mean. Okay, so here is my sort of quick trick to do this. So I know what tanth of 2 phi is. That's just this ratio of this U naught n and k's and things. I know that U and V are cosh and shine. So the strategy is to express cosh and shine in terms of tanth. Because I know that tanth is equal to this thing in terms of the physical parameters. So that's easy to do. I just say, well, cosh of 2 phi is equal to 1 over the square root of 1 minus tanth squared 2 phi. So that's because 1 plus tanth squared is sec squared or sec squared, whatever. And then I know that, so then I can say, well, in that case, V k squared is equal to UK squared. minus 1. And so that I can write as 1/2 of cosh of 2 phi k minus 1. So I now have a formula for v in terms of cosh 2 phi, and so therefore I can write that vk squared is equal to 1/2, and then it's 1 over 1 minus half squared of 2 phi k minus 1. And I know what length squared is because that's the equation star at the top of the page. And so therefore I can then just substitute in, and so let me then write for the final result. So substituting it in, what I get is the following two equations. UK squared is this. This is quite a complicated equation. That's U, and then V is given by a very similar thing. It looks like that. And this variable epsilon of k, we can just read it off, is h bar squared k squared over 2m squared plus 2n u naught h bar squared k squared over 2n square root. Okay, so none of that is obvious. What I did to derive that is for algebra. It's nothing very complicated. You can all do it, but that is the result. Okay, so now let's plug this back into our equation for the Hamiltonian. So step 6. So in the end, I end up with this form. So I end up with a constant piece. I end up with just my alpha k, alpha dagger, and they are multiplied now by this function epsilon that I've defined. And there's another piece that is left over, which I will write down. It's not very important, at least for now. And that is then epsilon k minus h bar squared k squared over 2m minus n u naught. And the reason I say it's not that important is because it's just a constant number that you can calculate. And so this whole Hamiltonian is then of the form some energy for the ground state plus the sum over k not equal to 0, epsilon of k, alpha k dagger, alpha k. And so now we look at this and we say, whoopee, this is great because this thing here is just the energy of a bunch of free particles. So these are these alpha particles. This alpha k dagger alpha k. This is just the number operator for the alpha particles at wave number k. So this is the number operator. So I've got the number operator of these alpha particles times the energy of those alpha particles. And so that is just the energy of a bunch of non-interacting particles. And this is some new many-body ground state. So that is the calculation. So again, let me just make sure that it's all written down in black and white. Energy of the ground state plus the sum over k not equal to 0, and then epsilon of k times the number of these alpha particles, k, and then this higher order terms that we've neglected. This is our quasi-particle description of the system. So that's great. So let's now examine what is the properties of the energy spectrum. So if you look at the functional form that we have over here on the left-hand side, what you can see is that epsilon of k, as k tends to 0, epsilon of k has the following functional form. It looks like n u naught over m square root times what happened again? H bar k, like so. And so I can write this as h bar c1 k, where this is the speed of sound. So remember, if I have a sound wave, remember, energy is h bar omega. So then I've got omega equals c times k, and so I can read off that this c1 is the speed of a wave. Of these phonons, and I can read off that the speed of sound is equal to n u naught over m square root. So these things look like this. So let's just remind ourselves what we started with. When we started with ideal bosons, I plot the energy as a function of K. So for ideal bosons, the energy dispersion relation looks like this. Okay, it's just going up like that, and this is the curve E is equal to h bar squared k squared over 2n. So it's a quadratic. But now what we've discovered is that if I now write down non-ideal bosons and plot the energy, so now these are weakly interacting bosons. So now what we've discovered is that the dispersion relation actually is linear at the origin, and then eventually actually starts to curve up like that. And so here at the origin, this behavior here is going as h bar c1 k, and so it is linear. And that's why we can think of these things as phonons. That's exactly the relationship that we would have if we had sound waves. And then let me just draw on here what we know, what we would have for superfluid helium. I showed you this last time. For superfluid helium, it also comes up like that. Then there's this dip here, and then it goes up like so. So this is what we have experimentally for superfluid helium. And so again, in superfluid helium, we have this h bar c1k. We have these phonon nodes. And so we've actually explained what is going on here. We've turned a quadratic dispersion relation for the ideal bosons into a linear dispersion relation at long wavelengths, and that is a consequence of the interactions in the system. So let's just see why we say that. So this form of the spectrum is an emergent outcome of the many-body interactions. So why do I say that? Well, the speed of sound is proportional to the square root of u naught, so it depends on u naught. That's the strength of the interactions. The only interactions in the system is the energy spectrum equals some complicated mess that depends on the interactions. And the energy of the ground state is n half n u naught plus some other terms. And again, this also depends on the interactions. So all of these phenomena that we're seeing go away when you turn off the interactions. They're true many-body effects. Okay, any questions about the energy spectrum?
I had a quick question about these quasi-particles. Just to understand physically, we do this calculation and we transform to the alpha variables, and we're doing a lot of math. Physically, where this idea of quasi-particle comes in is where we choose the UK and VK such that that anomalous term goes to zero. Is that the correct interpretation there?
Yes, that's the thing that we did. We forced it to be like that. Yes.
Okay, and then if you had one of these, if you had an actual BEC or something weakly interacting, and suppose you created one of these alpha states, what would it actually look like in a BEC? Is it just a sound wave, like we're talking about here, or does it look more exotic?
You can measure the sound wave, and you can measure the
Okay.
speed of the sound wave. And
Okay.
remember, so let me mention another thing. The quasi-particles are a linear combination of the AKs and the AK daggers of the real particles. And that's in Fourier space. So in real space, these quasi-particles involve all the particles in the system. So the quasi-particles are collective excitations of the system. So, I mean, yes, they look, so you can observe them by their effect. They arise from the way that we describe the system. But what we've shown is that at least within this theory, it is possible to find a non-interacting way to describe an interacting system. Okay. So now I want to talk about another aspect of this. Let's have a look at the energy of the system. So if I look at the ground state energy, so that is a thing that I wrote down before. So it looks like this. It's 1/2 n u naught times n, and then there was this term 1/2 the sum over k not equal to 0 of epsilon k minus h bar squared k squared over 2n minus n naught, like so. So that's the ground state energy of the system, and let's look at what this thing looks like. So what this is going to end up looking like is I'm going to convert this sum, then this sum that goes to v over 2 pi cubed times the integral d3k. So that's the density of states in k space. We talked about that before, and so what happens is this is going to be a term. If you look at, say, this term over here, this term is going to go like well, basically v d3k times say this minus n u naught, and d3k is just k squared dk times 4 pi, and so this whole term is divergent. Which is bad. So you say, okay, well, then now the whole thing is terrible. But the solution to this is you have to go to higher order. So now if you go to next order in perturbation theory, and I'm not going to go through that at all. And when I'm saying next order in perturbation theory, what I mean is I'm going to next order to perturbation theory in in scattering theory. So this is really quite non-trivial. So remember what we had seen before, that the pseudo potential looked like this: 4 pi h bar squared a over m. This is the result we had before for the pseudo potential. So we showed that the pseudo potential strength was related to the S wave scattering length. And somehow related to the cross section. Again, so I'm deliberately not going into the quantum mechanics of how you do that scattering. So that is technical, but we don't need to worry about it. I just want to tell you the result. So what Li and Yang showed was that actually there's a correction to this that comes to next order in perturbation theory, which comes in like this: 4 pi h bar cubed a over v times the sum over k 1 over v squared. And there's higher order corrections as well, and so you get something like this. And this this then this extra correction then allows you to compute the energy of the ground state. So then if you compute the energy of the ground state, what you end up getting is something that is finite. And it looks like this: 2 pi h bar squared a n squared over mv times 1 plus 128 over 15 root pi times square root. Actually, I'm not sure that this formula is correct. I think there might be a typo here. Give me 1 second. Yeah, there is. There's a typo. Okay, so this is the corrected formula. The formula that's in the printed notes has a mistake here. So so the typed notes were made from my handwritten notes, and the handwritten notes are more accurate than the typed notes, but the typed notes look better. So anyway, so this is the result, and this is finite. Okay, so why am I showing you these formulae? So what is the point about this? So the point is that this result shows you that we are basically doing an expansion in the quantity a cubed n over v. So that's what our dimensionless expansion parameter is. All of these terms here on the left-hand side, this is 1, this is some other term over here. Those terms are dimensionless. And so in order for this to converge and be a small change to the ground state when you switch on the interactions, what we need is that this term is small. And so in other words, what we're saying is, what this means is that a cubed is much less than v over n. And if I take the cube root of this, this is a is much less than v over n to the 1/3. And what is v over n to the 1/3? Well, this quantity over here is just the mean separation between the particles. So this thing over here is the mean separation between the particles. Between the bosons. And why is that? Well, a very simple argument. If I've got a volume V, and then I have inside that volume n particles, and this is a volume V is L cubed, then the number of particles per unit volume is N. So therefore the volume of the particle is equal to V over N, and therefore the distance per particle is equal to V over N to the 1/3. And so what we've basically found is that our calculation is self-consistent. In other words, the scattering length is much smaller than the interparticle spacing, i.e. the forces are very short range. So that is the result of the calculation. Any questions about this before I make one other comment about thermodynamics? Okay, let me just make a slight comment about thermodynamics, and then we'll come to the last topic. So what I want to show you is that actually what we obtained is very similar to what we would have got from thermodynamics. So I'm just going to very quickly breeze through this, and some of you who remember your elementary thermodynamics will see that there's another way that we see some consistency here. So let's have a look at our dispersion relation at small k. So I'm going to claim that the dispersion relation at small k gives you a speed of sound that is consistent with equilibrium thermodynamics. So if you don't remember your thermodynamics, just go to sleep for the next 2 minutes. So what we found was that epsilon is equal to the speed of sound, which I called C1, times h bar k. So that's epsilon of k. and if I were to, what does thermodynamics tell me? So thermodynamics says that if I know the pressure as a function of density, then that gives me that P is a function of density. Rho is just n over v, that's the number density times the mass of the particles. So C1 squared is equal to dP by d rho, which is 1 over n dP by dn. So that's what thermodynamics gives you. So that's just standard formula from thermodynamics. Now, on the other hand, the pressure is just given by the rate of change of the energy with the volume. Okay, if I take a system with energy E, I change the volume by V, that will then increase the pressure. If I reduce the volume, the pressure will go up, and what we mean by pressure is just dE by dV. And so I can just take my dE by dV. I know what the energy of the ground state is, so that is over here on the left-hand side. But the lowest order term is just simply that, and so dE by dV is just 2 pi h bar squared a n squared over m v squared, which is equal to 2 pi h bar squared over m times a times the number of particles per unit volume squared. And so therefore, I compute the speed of sound. That is then 4 pi h bar squared a over over what? Why did it say on what? Which is just U naught n. Oh, and again, another typo in my notes, and this is exactly what we obtained before for the speed of first sound over here. Where is it? Over here. So what I've shown you is I can calculate the speed of first sound in two ways. I can calculate it directly by reading it off from the energy as a function of K, and I can calculate it from the ground state energy of the system by using thermodynamics. So thermodynamics and the dispersion relation both give you the same answer. Which is a very interesting measure of consistency. Okay, so we are nearly finished with today's lecture. I want to just very quickly start the last topic. I'm not going to do a detailed calculation, but I want to tell you what happens to weakly interacting bosons at non-zero temperatures. So what I will show you the result is, I'm not going to go into huge detail with the calculation. I'm going to ask what happens when we raise the temperature. So when we raise the temperature, then some bosons are excited out of the condensate. And so we call that depletion. Okay, the condensate is depleted. So what you might say is, well, we can calculate this in the following way. I can say, well, what is the depletion of the condensate? Well, if I take the number of particles in the system minus the number of particles that are in the ground state of the system, which is a function of temperature divided by the total number of particles, that is what we mean by the depletion. So that's the depletion. So it just says that these are the particles not in the condensate. Okay, so how do we calculate that? Well, we know how to do thermal expectation values with annihilation and creation operators. You did that in the second quantization worksheet, so one can in principle do this calculation. Now, what you might have expected is the following. What might we expect for this? And the answer is, well, remember that the condensate is what gives us superfluidity. Here we saw that last week. So if the condensate gives us superfluidity, then we know that the superfluid wave function stiffness is given by the superfluid density, rho s. And just to remind you, why do I say that? Well, if I think of the velocity of the kinetic energy of the superfluid velocity, that's a half rho vs, and that is 1/2 rho times h bar over m squared gradient of the phase of the wave function squared. So we saw that last time, and so this thing here is like the stiffness of the wave function. Okay, so we called rho s the superfluid density. We also called it the helicity modulus. So the superfluid velocity is just given by the gradient of the phase of the macroscopic wave function, and so we would expect then that the quantity that gives us superfluidity then is related to the superfluid density. So if that's the case, then what you would say is, well, in that case, the number of particles in the ground state divided by the total number of particles should be equal to the density of the condensate of the superfluid state, rho s, divided by the total density of the system. So that's what we would expect. And therefore that would tell us then that the depletion of the condensate is nothing more than rho n, normal fluid density, divided by rho. So that would be a thing that we would expect. And it's something that connects what we have in the microscopic theory of the interacting bosons, and it connects that with the phenomenological aspects of the superfluidity, the superfluid state, the superflow, the helicity modulus, and so on. So that's what we would expect. And we can calculate both of those quantities. And what I'm going to show you next time very quickly is that this is not indeed true. It's not. This is not what happens at all. So this simple picture isn't correct, and we'll see what that means next time. Okay, so that's where we'll stop for today. Any questions about today's lecture? Let me first of all turn off the recording.